Hello everyone, welcome to Design Hub. In Design Hub, we provide quality technical content related to the design industry using practical concepts. So, to upgrade yourself, please subscribe to the channel and press the notification bell to get notified every time we drop a new video. In this video we will do a static stress analysis of CAM and follower. First, let's see the problem statement and make required assumption for the study. The problem statement of this study is to determine stresses in the reciprocating CAM follower. We have to find the stresses in the ringed area around the roller arm's upper end, where it passes through its support in the frame, which is to be specifically determined. The CAM and follower positions in the figure are taken to correspond to the location of the CAM follower's maximal pressure angle and dynamic load. However, a dynamic analysis should be carried out using Solidworks motion and the consequent loads imparted to the model. We know the CAM follower's measurements. As evidenced here, CAM applies 368 newtons of force to the follower in the x direction, as well as to the roller pin in the y direction, at the bottom of the follower with a magnitude of 1010 newtons. Since a static stress analysis will be conducted, the upper end of the roller arm is assumed to be fixed, exactly like the cantilever beam, and the appropriate reaction forces are displayed here at the upper end of the roller arm. Additionally, you will soon see in subsequent videos why the solid tetrahedral parts are an exception to this rule. This is a simplified form of the follower's arm modeled in SolidWorks. Now, let's see what strategy we will follow. The strategy for this problem will be generating high-quality mesh to get accurate results and obtain deformation curves after the results. Even though the finite element method is a potent computational technique, engineering assumptions that might improve the entire design process should always be taken into account. We shall make three possible assumptions in this section. The range of potential materials is first whittled down to a subset that offers a strong but heat-treatable class of steel. The contact between the CAM follower and the frame in which it slides must have a strong, long-wearing surface. We may omit modeling of the roller and its pin connection to the follower since our main focus is on static stress analysis at the top half of the roller arm. It will help us save a lot of time and modeling work. Additionally, we'll assume that the roller arm's upper end is fixed, which will ultimately simplify this exercise considerably. Now, the first step we will follow is to make the model in SolidWorks according to this figure here, or you can download this file from GrabCAD. And you can start the study by going in Simulation and create new study. Let's jump into SolidWorks and start the modeling of follower's arm and create the static study. Before you start with the analysis process, it is important to set the units for SolidWorks simulation. Set the default unit according to your preference. Step 3 is assigning a material. Choosing a material is a phase in the design of any physical thing. The major objective of material selection in the context of product design is to minimize costs while achieving product performance goals. The material we will use here is AISI 1045 steel. Medium tensile AISI 1045 steel is offered in hot rolled or normalized black color. This material has a yield tensile strength of 530 megapascals, an ultimate tensile strength of 625 megapascals, and a Brinell hardness of 170 to 210. In either the normalized or hot-rolled condition, AISI 1045 steel exhibits high strength and impact properties as well as good weldability and machinability. For all industrial applications needing greater wear resistance and strength, AISI 1045 is frequently employed. Examples of typical uses for AISI 1045 are gear, pins, rams, shafts, rolls, sockets, axles, spindles, etc. So, let's assign AISI 1045, cold-drawn steel to the model. It is important to save the model before starting the simulation. We will create a new study named as CAM Follower Stress Analysis. As we talked about it before, that the upper end of the follower's arm will act as fixed support. We will apply the fixed support at the top face of the follower's arm. Step 4 is applying the load to the model. In this static study, the load exerts at the bottom center of the follower's arm. The force from the cam is transferred to the roller, and then to the arm in both X and Y directions. In order to achieve that, we will create a split sketch at the bottom face of the follower's arm to apply the loads precisely at the bottom center. We will see it in Solidworks. If you have a load in kilograms and want to convert it to newtons, then just multiply that number by 9.81. Now, we will one by one apply the load in both X and Y direction at the bottom center of the follower's arm. We will first create the split sketch on the bottom center of the follower's arm. First, we will apply force Fy with magnitude of 1010 newtons in a reverse direction, which we do it later to see how it impacts the geometry of the follower's arm. We will select the split sketch edge for the force and after select the another edge for the force direction. Similarly, we will do it for force, Fx, which has a magnitude of negative 368 newtons. Select the split sketch edge for force and another edge to give direction to the force Fx. Step 5 is about generating a high-quality mesh. We will be using high-quality standard fine mesh in this study. You can see the details of the mesh in this Mesh Details dialog box. These are first-order elements, also known as draft quality elements. After deformation, all the faces and edges remain straight and flat. Surface, solid, and line elements are present in this. Elements might be quadrilateral or triangular in shape. When meshing a challenging shape, triangular pieces are typically used, but quadrilateral shapes typically perform better. Depending on the case and how much you want to simplify the problem, you can choose the ideal element for the model. High-quality mesh has the type of element that is mid-side nodes to get accurate results due to curves after deformation. The sixth step is to run the study after all the essential steps are performed. Also, prediction and comparison of the results will be performed. Here, in this study we will be doing stress analysis. We will run the study. Like I mentioned before that we will reverse the direction of force Fy later. You can see the impact it has on the geometry of the follower's arm. Now, we will run the study once again to apply the changes. First, we will predict the result via classic stress equation. In this study, force component in the x direction causes bending that produces tensile stress at point C, and compressive stress at point A. And the upward acting force Fy equals 1010 newtons, causes axial compression throughout the length of the follower's arm. The standard stress equations imply that this stress is evenly distributed throughout the model from top to bottom, despite the fact that it is depicted near the lower end of the cam follower. You can see the bending stress and axial stress calculated. A similar bending stress is produced by the x component of force, Fx equals negative 368 newtons, which acts perpendicular to the length of the cam follower as indicated. Due to the maximum length of the moment arm being acted upon by the x component of force Fx, which is applied at the bottom of the cam follower, the bending stress is greatest at the top of the model. Since all of the stresses shown above are in the y direction, they may be merged by simply combining the axial and bending stress magnitudes as long as the correct positive and negative signs are present. The results of adding these stresses are displayed.
Now, we will see stresses at points A, B and C.
Due to axial and bending loads, the stress at A is in compression. As a result, the total magnitude we will obtain is equal to a negative 37.35 newtons per millimeter square. Axial stress is causing compression at B, but because bending stress is on the neutral axis, it has no effect. As a result, we will have a value of negative 3.13 newtons per millimeter square. Due to axial stress, the stress at C is compressive, while bending stress causes it to act in tension. Because the compressive axial stress is lower than the tensile bending stress, the number is 31.09 positive newtons per millimeter square. Now, first, we will perform and examine the results using a probe tool, and try to minimize the percentage difference between manual calculation and FEA results. It is frequently desirable to identify the stress magnitudes at particular areas, even while stress contour plots give an overall idea of stress magnitudes throughout the model. The model's picture is altered by superimposing a mesh to make it easier to choose particular points on the model. We are going to compare simulation results to results from the classic stress equation. And also, we will calculate the percentage difference between the results of FEA and results prediction form manual calculations. St. Venant's principle, which asserts that stress anticipated by traditional equations exists only in regions sufficiently well separated from a. points of load application, b. support locations, and c. locations of geometric discontinuity, provides the answer to the aforementioned question. Any of these circumstances frequently has a major localized impact. Accordingly, in certain places, the limitations of the classical stress equations conflict with the more precise outcomes anticipated by finite element approaches. In order to select nodes at positions a little bit farther from the top support site, the probe tool is once more employed. Go ahead as directed. First, we will edit the stress plot as y normal stress plot, and change the deformation scale to the true scale to get unexaggerated results. Also in the property option, select include title text and name it sigma y. Now, go to the settings, and change the fringe options from continuous to discrete in order to see the stress contour plot more clearly. We have to change the chart format from scientific to floating in order to see the result values clearly. Also, we have to superimpose the mesh on this discrete stress contour to be able to calculate the results accurately. Now, we will use the probe tool at entities, and plot the graph for the top edge of the follower's arm. You can see the great percentage difference between the manually calculated stress results and probe tool results. Select the probe tools and choose Probe. In the Options section, choose on Selected Entities. Now, we will select the top edge of the follower's arm. Due to the high-quality tetrahedral elements having nodes at both corner and mid-side locations on each element, there are a total of 31 nodes present along the top edge of the model. Note the maximum and minimum values of stress from the summary section, and value of stress at the neutral axis. Plot the graph from the report options. Now, we will use Probe tool and choose, at location from the Options section so to see the stress exerted at that particular node. You can now see the percentage difference in this plot. It is significantly very less than the previous one. Do further procedure as directed. Select the required nodes, and plot the graph. And compare it to the previous one. To differentiate the graphs, go to Options, and Properties. Now in Titles section, go to Label and name the graph as Combined Axial and Bending Stress. Also, you can name the axes accordingly as shown here. Let's examine what other observations were included and what FEA relevant assumptions were made before wrapping up this video. Localized conditions, sometimes referred to as end conditions or boundary conditions, can have a substantial impact on the outcomes of finite element analysis, when they occur at the places of support, applied loads, and/or geometric discontinuities, locations of stress concentration. Typically, the traditional algorithms employed in manual stress estimations cannot foresee these impacts. Because of this, Caution must be taken while examining finite element results in these areas. At places far enough from localized conditions, finite element analysis and manually computed solutions often show great agreement, St. Venan's principal examples. It cannot be emphasized how crucial it is to choose the appropriate stress in a finite element analysis when comparing results. In the case of the CAM follower, for instance, the von Mises stress default plot from SolidWorks simulation does not, and should not, correspond with manually derived values of stress in the y direction, sigma y. To put it simply, stresses must be compared when examining the reliability of results from finite elements. Thanks for watching. Until then, learn and grow.